Hi, this is Mr. Ward, and I'm going to talk about Chapter 10.4. Now, Chapter 10.4 is broken into some parts. There's a Part A, there's a Part B, there's a Part C, and there's a Part D, which all focus on different elements of the same basic idea. So we're introducing some new types of lines that are related to circles. One is called a secant, and the other is called a tangent. And you've got some definitions here. So a secant is a line that intersects a circle at exactly 2 points. Okay, every secant contains a chord of the circle. So here we have a secant with line AB as a secant. It makes a chord AB. It intercepts, of course, an arc AB, but that's the secant. The tangent is distinct from a secant in that it intersects the circle. Tangent intersects a circle at exactly 1 point. And tangent lines are important in a lot of mathematics. With circles, of course, you'll run into them a lot when you get into calculus, of course. But with circles, they touch at 1 point, and that point is called the point of tangency or point of contact. Now, here's a really important concept about the tangent line. It is perpendicular to the radius. So if we have a radius drawn to the point of contact, it is going to be at a right angle to the tangent line that contacted there. And if a line is perpendicular to the radius at its outer endpoint, the outer endpoint being where it touches the circle, then it's tangent to the circle. So that's the first postulate. This postulate said in the opposite direction. So here, a tangent line is perpendicular to a radius drawn to the point of contact. So it needs to be a radius drawn to the tangent, point of contact. And if a line is perpendicular to radius at its outer endpoint, which means where it touches the circle, then it is tangent to the circle. All right, so that's the basics of Part B. Now we're going to take a look at Part A. Let's take a look at Part B. So we have the concept of a tangent segment, which is a piece of a tangent line, and it's going to be between a point of contact of the circle and some other point on the tangent line. So that is a piece of a tangent line that includes the point of contact and all the points between that and some other point on the line of tangency. So that's also going to be perpendicular to a radius. A secant segment is going to join some point that's outside of the circle with a chord. So basically, you take a chord and extend it in one direction. You have an external part and an internal part. So that is what's going on with the secant segment. The external part of the secant segment is part of the secant line that joins the outer point to the closer intersection point. Okay, so hopefully that's fairly straightforward. Okay, now we get into some theorems. If we have two tangent segments drawn to a circle from an external point, then those segments are congruent. This is called the Two Tangent Theorem. And this is going to be really useful in proving a lot of congruency because point P is going to be equidistant to X and Y, the points of tangency. So you have some point out here, and tangent lines are drawn through it to different parts of the circle. Those tangent lines form tangent segments that are congruent. All right, let's see if we can prove this is true. We're going to prove PX and PY are congruent. Well, let's see what we've got. I'm going to pause this. So remember that the radius at the point of tangency makes a right angle. So this forms two right triangles. And also, let's note that OY here and OX are radii. And then we can also use the no-duh theorem that OP is itself. And now we have two right triangles with a leg and a hypotenuse that are congruent. So we can use hypotenuse leg, and then we can say very easily that XP and YP are congruent by Kappa-Kadaka. Now let's consider some further things. That's part B. Let's deal with part C. Tangent circles. Circles can be tangent as well. And you can have circles that are tangent where they touch, and also circles where one is inside another one, and they're tangent where they touch. So they touch at exactly one point. You can have externally or internally tangent circles. Now, let's consider some implications of that. Actually, I want to go back over here. So notice that the centers of those two circles connect with a segment that goes through the tangent point. And that's true for the internally tangent or externally tangent circles. All right, finally, let's take a look at part D. Sometimes you have two circles that are not touching, and you have this thing called a common tangent. So they could be touching, but they're not necessarily. So a common tangent is one line that's tangent to two circles, not necessarily at the same point. Moreover, the tangent is a common internal tangent if the tangent lies between the circles. It's a common external tangent if it lies not between the circles. So AB is externally tangent, and AY is internally tangent because it's between the two circles. So these are important definitions that we'll get into. Notice that we only have one theorem that we've been given so far. In the next section, in 10.5, there will be more theorems about this. All right, in my next video, I will walk through some of the sample problems and some techniques for doing some solutions. And for now, I will